everyone to this PyTorch Bootcamp course. This course should teach you everything you need to know to get started with PyTorch. And I will not only show you how to code a simple neural network, we also look at some of the underlying basics of training and evaluating models. At the end of this course, we also have an exercise that you can try to finish it based on what we learned. Now the prerequisite you need is some Python skills. And if you use NumPy before, it's gonna be perfect. However, I will not explain deep learning concepts like backpropagation and how neural networks, what is optimizer. So if you want to learn more about this, you can refer to some deep learning like documents, videos, or enroll the machine learning unit. Okay, let's get started. PyTorch, what is PyTorch? PyTorch is an optimized tensor manipulation library that offers an array of packages for deep learning. So you may know some deep learning package, for example, the Google TensorFlow. So the Google TensorFlow, it is static frameworks. So what is static frameworks? It means you need to define the entire computation graph first. For example, you say, I will add A and B. A and B maybe is vectors or metrics. Then multiply the result by C. Then compute the loss, then do the backpropagation. And after you define the graph, you compile it into an optimized form. Then you run it using input data. So it has pros and cons. The pros is once compiled, it's very fast. You just need to give the input data, and then this will calculate based on the graph you compile. But the bad thing is it's very hard to debug, and it's not flexible. You cannot change the graph easily while running. But PyTorch is a dynamic framework. So which means you don't need to build the computation graph in advance. It is built on the fly as you run the code, and you don't need to predefine or compile anything. You can use Python's control flow inside your model easily. So the process is super flexible and it's great for research and some experiment. So that's why now the PyTorch become more and more popular in academic research. But the cons is because the graph is created every time during acquisition, so it can be slower and less optimized than static graphs. So if you want to build for example, a deep learning mobile or production, then maybe TensorFlow is a better choice. But here, because we focus on some like research and how the models works, so here we use PyTorch more. And here is an overview of this bootcamp. We start from installation, and then we introduce some tensor basics, such as how to create tensor, the operations like add, multiply, and some other important operations, and GPU support, like how to move the CPU tensor to GPU to speed up your model training. Autograd, training the pipeline, like how we define the PyTorch models, optimizer laws, and how we train the models. And later I will show you how to build a simple neural network by using PyTorch with GPU support. And at the end, I have an exercise for you that's to help you to better understand the concept we learned today. Okay. So for installation, you can just go to the pytorch.org website and scroll down here. You're gonna see is then you can select based on your select your configuration. For example, my OS is Mac, but maybe yours is Windows or Linux. And package, usually we choose pipe. And language is Python. And if you have GPU support, then you can choose CUDA, then the CUDA version. If you're not, you just choose default. Or but usually when you go to the website, they give you the default selection based on your device. And then you just copy this command and then pass it to, if you are using Windows, then you go to command line. If you are using Mac or Linux, then you can go to terminal and then pass this command and run it. It's gonna install the Torch library for you. Or the easiest way to get started with it is just to use a Google Colab, because PyTorch is pre-installed in Google Colab. So here you also get a free GPU. So in my opinion, it is the easiest way for you to get started. Okay, if you're not using Google Colab, you will install it on your device. Then after you pip install all the packages, and then you just go to some Python editor and import Torch. Oops, sorry, I should change runtime, GPU, save. And you import Torch. And if you didn't receive any error, which means PyTorch has been successfully installed. And if you want to see if your Torch support GPU, the CUDA, then you just use this function. It's torch.cuda.is available. And then if it's return true, which means okay, you have the GPU support for your PyTorch. If it return false, then which means all your PyTorch operations or your models have to be in CPU, which is very slow when you have a lot of data and a huge model. And the next part is some tensor basics. So everything in PyTorch is based on tensor operation. A tensor is a mathematical object holding some multi-dimensional data. It is very similar to NumPy ND array, but here also have GPU support. And because it's multi-dimensional, so we can have different type of tensor. For example, if it's only have, sorry, if it's a tensor of order 0, then it's just a number like 1, 2, 3, 4, 1, 2, 3, 4, 5, and usually we call it scalar. And if it has one dimension, then we call it a vector. In mathematics, we call it a vector. And if it has two dimension, then we call it a matrix. So it's and if you have three dimension, then in the visualization, it looks like a cube, but actually it's just a sequence of matrix. So you can think is this layer is a matrix, and behind this layer is another matrix. So it's a sequence of matrix. But definitely you can have higher order tensor. So it's like n-dimensional array of scalars. And in NLP, usually we have three-dimensional tensors. So for example, when we want to input the data to the models, we have a bench size, right? The bench size is every time how many sentences or training samples the model can see. So it's based on your GPU capability. So if your GPU is has enough memory, then you can have a very large bench size. If it's not, then maybe your bench size is just like 4, 8, or 16. And the second dimension is sequence length. So it means for each sentence, how many words is in this sentence. Okay. And the embedding size is the embedding. So like in NLP, maybe you'll learn like the vector, the embedding like word to vec or BERT is like each token. For example, if the embedding size is 100, which means each token or each word is represented as a 100D vector. Then this tensor have three dimensions in the shape 16, 10, and 100. Okay, this means, okay, for each input for the model, we have 16 sentences and each has 10 tokens or 10 words, and each token is a 100-dimensional vector. The second part is the creation. So how we create tensors, we have different ways. So we can see here, the first way is we can create tensor from some PyTorch functions. The second way is we can create from Python list. And another way is we can just create tensors from NumPy. We will look at one by one. So first, if you want to create tensors from PyTorch functions, then you can using the tensor function. The tensor function, you can create either a scalar or a tensor. So it means you can use this one to create any dimension, a tensor with any dimension. The PyTorch tensor have equivalent functions as its NumPy counterparts, like ones, zeros, random, and many more. So ones means you fill the vector or fill the tensor with one, number one, and zeros means you fill the tensor with zero. And the random means you random generate some tensors or vectors, but these two are two different distribution. For example, the first one, the rand, is mean you want to generate some random vector on uniform random. If you use random n, this is normal random. Okay. Okay, then let's see the code. So first you import Torch after you install the Torch in your device. And for the scale, you just call the tensor function. So it's torch.tensor. This is the function that PyTorch provided. And this is the scalar, just a number. So here, which means I create a tensor, which is just a number, and it's 3.14159. And for vector, which is have two dimension, right? So here you can see I have a list of number 1, 2, 3 is a list, and this is gonna be a one-dimensional vector. And for matrix, so for matrix you have, if you want to use the function torch.once, and then you just give the shape you want. So the first number here is the number of rows, and the second parameter here is the number of columns. So the matrix 2 means you want to create a matrix with 2 rows, 3 columns, and the D type is the float number, and you filled each cell with 1. And the second method is you doesn't want to random generate or use ones or zeros functions. You want to create based on the list of lists, nested list. Then you just pass the nested list to the function torch.tensor, and then you define what D type you want. You can have integer, you have float, and then sorry, this is not fill with 1. This is just to create a tensor with this value. And this is for matrix with 2 dimensions. So how about we want to more dimension? Then you can use random. Then this means you want to create 2 3x4 matrix with D type float. And then you print it. You can see this is the tensor you just created. So it's So for more information about D-type, the D-type is similar with NumPy D-type. If you want to see what D-type that PyTorch support, you can go to this website. So they have float 16, float 32, integer, and so on, and also have Boolean. Another function that we always use is torch.empty. So torch.empty is a function in PyTorch, allocates memory for a tensor, but doesn't initialize its values. So which means the value you see are just whatever was already in the memory at those locations. They are essentially some garbage values or random leftovers. So you can see every time if I run torch dot sorry, you have to So you can see if every time I run torch.empty, it's gonna give me different values because just some random value from your memory. Another thing you need to be careful is the capitalization. So we know when we just coding like Python or other programming language, we may make mistake on the capitalization. So in the examples above, we use the tensor with lowercase, so it's lowercase t. but you may sometimes make mistake and make it T to uppercase. And then you will find actually they both can generate tensors, but they are very different. So for the first one, which with capital T refers to a class in PyTorch. The class is torch.float tensor. So even though here you can see a passed integer is 2, 3, they are integer, but when you use the uppercase T, and the result is float because torch.tensor refers to torch.float tensor class. But the one with lowercase t, on the other hand, infers the D type automatically and alone specification of D type during creation. So you can see here I have torch.lowercase tensor 2, 3, and the result is just some integer that meets my input. So when you create tensors, you should use torch.lowercase t, not the uppercase t. And after you create tensor, sometimes you want to check the size, like the shape. So there are two methods you can use. The first one is size, and the second one is shape. But they are different. They do the same. They can return like same result, but they are the different functions. So first you can see I create a vector, a field with 0 with 5 rows, 3 column. So you can see it here, a tensor. And if I use size, you can see I have a parenthesis. So you remember in Python, if we have a object dot a name with parentheses, which means it's a method in your class. It's a function in your class. But for shape, you can see I didn't have any parentheses or bracket after it, which means this one is an attribute in your class. So even though they can retain the same result, but size is a function, is a method in the torch class, but shape is a property. So that's why you can see size have the parentheses, but shape doesn't have. Okay, and you can if I use x dot size parentheses, they return me 5, 3, and if I use shape without any bracket or parentheses, it also return me 5, 3, return the same result. But if you want to get the dimension, the number along some dimension. For example, I want to know how many rows I have, then it's also different because size is a function. So you also use the parentheses and then the index. So 0 means the first one. So it's the number of rows. And if you want to get number of column, then you just replace the 0 with 1. So then it's going to return 3 in this example. For the shape, because shape is a probability, so you cannot use parentheses. That's why here is the square bracket. The square bracket, and then you have, if you use 0, means you want to get number of rows. If you use 1, means you want to get the number of columns. Here is 3. Okay. Another function, another attribute is not function you can use is to check the data type. So sometimes after you create the tensors, maybe you forgot what the data type it is. Then you can just use dot d type. It also is it's a attribute, so you don't need to have any parentheses and a bracket. So for example, you can also specify the types when you create a tensor. So for example, x equals to I use zeros function, create a matrix with 5 rows, 3 columns, field with 0, and the data type here is float 16. Okay, and also you can specify, for example, torch dot float 32. So the difference between float 16 and float 32 is a precision. So 16 gonna take less memory, which I think is only take 2 bytes, But for float 32, it's gonna take 4 bytes. It's gonna be more precise, but also float 32 gonna take more memory and maybe it's like the GPU and so on. Okay, and when this time when you specify the types, when you create the tensor and then you print it, you can see it say it give you the tensor x and then the d type is float 16. And also you can use x.d type to check the d type, so it's float 16. If you didn't specify the d type, then the default gonna be float 32. Here, I defined a function that I'm gonna use later. I defined a Python function. So every time it's input a tensor, I want to know what the type it is, shape and size. Actually, they are doing the same thing. And then I want to know the value of the tensor. This one I'm gonna use it later. So just to write the function to make my later demonstration easy. Any question for creating tensors from PyTorch functions? Okay. So if you don't have any question, we can move to another way to create tensors is to creating tensors from list. So actually, I already gave example in the previous section. So if you have a list like this one, I have a nested list 1, 2, 3, and a second list 4, 5, 4, 5, 6. I want to convert the list to tensor. Then you just use the torch that tensor method, and then it's gonna convert this one to a tensor. So here you can see I have x equals to torch.tensor 1, 2, 3, 4, 5, 6. And when I use a function I just defined, it returns I should wait a sec, I should write again. So if I use, it's gonna return, okay, x is the d type is long tensor. Long tensor means integer. And the shape and size are the same. They are 2 by 3, 2 rows, 3 columns, and the values is a tensor 1, 2, 3, 4, 5, 6. And if you are using the so here, if I'm using the uppercase T, remember, which means it refers to torch.float tensor class. Then if you run it again, you can see the difference is that each items in the tensor become float. It has a dot behind it. So which means that the D type is a float tensor. Another way creating tensors is from NumPy. It is useful when you, for example, you load some CSV by using NumPy functions, and when you train the model, you want to convert these NumPy vectors or array into PyTorch GPU support tensors to speed up your training. So this is also very some useful functions. If you want to creating tensors from NumPy, we have 3 methods. I will show you one by one. So the first one is from NumPy function. So here I first create a NumPy array. It look like this here from 0 to 9. And if I use torch.from NumPy function and then I use describe to print it, it's here. So it's a long tensor D type, which means each element is integer. And the size is 10 because just to have one dimension, and size also 10, and the value is lowercase t is tensor with this value. And also you can use this one with uppercase T. So which means you wanna create a tensor with float tensor. So here you can see this is the output. So if you use the uppercase T, then the D type is float tensor. and the same is size 10, and the difference you can see is tensor. Each element in the tensor has a dot, which means they are float number. Another way is to use the torch dot tensor with lowercase t. So this one is exactly same with from NumPy. So this is here is a result. You can see this one is exactly same with the first one. So they two have the same function. Another function is you can use the function called asTensor. So if you use asTensor, actually it's also doing the same thing as the from NumPy and torch.tensor. But these three methods is you can ignore this one. Let's ignore the one with uppercase T because this one is just to show you the difference between uppercase T and lowercase t. So if you want to convert a NumPy array to PyTorch tensor, we have these three methods from NumPy, tensor, asTensor, but they also have slightly different. If you want to avoid data copying when converting from NumPy to PyTorch, use from NumPy or asTensor. These create a tensor, they share memory with original NumPy array. So which means if you change the original NumPy array, the tensor also change. I will show you the example later. But if you wanted to create a new independent copy of the NumPy array as a PyTorch tensor, use torch.tensor function. So this one will copy the data into a new tensor. And if every time when you update the NumPy array, it will not affect your tensor. I will show you the example. So the example is here. First, we import torch, import NumPy libraries, and I create a NumPy array with 1, 2, 3. And I want to convert this NumPy array to tensor without copying. So I have two methods from NumPy asTensor, and it's I use T1, T2 to record the results. Another way is the third method is I can convert a tensor with copying by using torch.tensor method and save it to T3. And now I want to modify the original NumPy array. So this means I want to update the first item into 100. So because T1, T2, this my from NumPy asTensor, they are sharing the same memory. So if A is changing, then T1, T2 also. But because T3, which create from torch.tensor, T3 is not sharing the memory with A. So if you update A here, T3 doesn't change. So you can see here the result. The original NumPy array is after the update become 10023, and T1, T3 also become 10023. But for T3, which use the method torch.tensor, it's still 123. The first item must not change. And you can also do it in the other way. So we see how we convert from NumPy to torch tensor. You can also convert torch to NumPy. So by using .numpy method. So for example, I create a torch tensor filled with ones, and this is what it looks like. And I just a.numpy function and then print b, then you can see b become a numpy. This is how we convert between NumPy and PyTorch. Any questions so far? If you don't have any question, we will move to the next section is reshaping a tensor. So reshaping tensor is important for many reasons. First, it helps manipulate data to fit the input requirements of models, change data structures for easier computations, or optimize memory usage. So for example, we know that in mathematics, the matrix multiplication follow the rules, right? If you want to multiply two matrices, say A with shape n by m, B of shape m by p, the resulting matrix after the multiplication gonna be n by p. So which means the second dimension of A have to be exactly same with the first dimension of B. So, but if you have two tensor matrix and these two are not the same, then you can use reshape to make them into the same dimension number. And another example is in data preprocessing, you might want to reshape tensors for augmentation techniques. For example, tensors actually can representing image, right? The pixel for each pixel, like each tensor can represent the pixel of the image. So if you are reshaping it, actually you are reshaping the image. For example, flipping, rotating to enhance the model generalization. So reshaping helps adjust data for these transformations. Another reason is for convolutional layers, usually requires a full dimension tensor with shape bench size, channel height, width, while fully connected layers usually expect two dimensions. So with input features with output features. So reshaping allows you to convert data from one shape to another to fit the model's requirements. And how we can reshape? It has two methods. One is use the function called view. Another function is reshape. But here I will suggest you to use view because the view method only returns a tensor with the desired shape that share the underlying data with original tensor. It doesn't create a new independent tensor. So which means every time if you change the original tensor, the resulting like after the view function, the resulting variable also change because they are not independent. But for reshape, it's due to some reason, it may or may not create a copy. We don't know it. The reason behind this is a bit weird, but it's beyond the scope of this section. So because of this reason, then view is preferred. And let's see how the view works. So first, let's define a matrix with a like 2 by 3 matrix with 2 rows, 3 columns filled with 1, and the D type is float 32. And when you print the matrix, it looks like this. So it's like 3 rows, 2 columns filled with ones. And now I want to reshape this matrix with 1 row, 6 column. So I use matrix dot, the matrix of variable name dot view. This is a function and the shape I want. So it's 1, 6. And then I save this result to a variable called same matrix. And now if we want to change the elements in the same matrix, so for example, I want to change the first row, second column from changing from 1 to 2, then I just assign it to 2. And now if you print the matrix and the same matrix, you can see they both change, right? Even though the changing is on the same matrix, but the matrix also changed. It is because they two are sharing the same memory, just like the from NumPy example we see in the previous sections. So you may have the question like, okay, how about I just want to reshape it and then, but I don't want them to share the same memory. Then you can use a clone method. So the clone method is, so here I also defined a matrix with the same shape, 2 by 3 and filled with 1. And this is the matrix look like. And now after use the view function to reshape it to 1 by 6, I use clone. So clone means now the matrix and the same matrix not sharing the same memory at all. So now if I update, for example, I say for the same matrix, I will also change the first row, second column to 2. And if you print matrix and same matrix, you can see the matrix is not changing, but the same matrix is changing. This is because now the matrix and the same matrix are not sharing the same memory. Another one is creating with autograd. This one we're gonna see more example later when we look at the GPU section. So this will tell PyTorch that it will need to calculate the gradients for this tensor later in your optimization steps. So which means this tensor is learnable. before all the tensor we defined, they are not learnable. They're just fixed. You can see every time if I want to update, I have to manually update by given the row index, column index. But in machine learning, actually, we want this tensor to be learnable. So which means every time after the forward computation and the back propagation, I want to update these tensors based on the loss function optimizer. So when you create a tensor, the first part is same. You still use torch.tensor method and with the values you want. But here you can give for the function requires grad equals to true. So now when you print the x, you can see we have a another attributes requires grad equal true which means this tensor will calculate the gradients later in the optimization steps. It's learnable. It's not static. Okay. Second part is operations with tensors. So in the first part, we already see
Hey, wait
how
a
we
minute.
can. Okay.
So what's the question? Wait a minute.
Oh, we have question. Okay.
What's the question? Yeah. Sorry. What's the question?
She refers to a static tensor.
Yeah.
So is that the same as being immutable? Elements of are immutable.
So you mean whether the tensor is none?
Well, immutable, you can't change the elements unless you have this grad requires grad equals true.
This is not about. This is a different concept than the whether it's mutable. That's a concept in the Python, right? So this one here is in the neural network. So back propagation, you're trying to do this gradient and going backwards calculation. So this one is saying if you put it there equals true, means later when you're trying to in the training in the later when Thread was trying to describe how to use the optimizer to do the calculation, then these kind of tensors we're doing that like a neural network calculation and update the value of it.
So you change the values.
Yes, yes, and it's nullable. That's basically why it's powerful. Yeah. Yeah. I think you can continue. Sorry, there's.
That's all good. Thank you, Pascal. I think this question from Peter, right? Peter?
Yeah.
I think Peter asked about the changing things. Yeah, I think Pascal is on the point is because when we're training the models, these tensors actually refers to the weight in your neural networks. So you want this weight to be updated after back propagation.
Yeah.
So but that's why we set the requires grad equal to true. So they are learnable. But if you didn't set this to true, they are just some fixed vector, fixed number. They will not change at all, even though you do the back propagation and learn the gradients.
Yeah, but if you really want to update it with a Python program, you say give this one another value for that variable, you can do that. That's two different concepts there. One is about the calculation, the weight of it, and just the variable give it a value. That's two different.
But in both cases, you're updating the tensor.
It's a bit different. Like answer, you actually hold status of it, like the gradients, how you doing the calculation. So it's a class. It's a more comprehensive class rather than the value zero.
Understand?
Yeah.
Okay.
Yeah. Okay. All good. Then let's go move on. So the next one, okay, now we have see how we create tensors, and then we want to do some operations with tensors. So this one just some operations that you learn for the metrics. For example, here I first define two metrics. The first one is a matrix with two rows, two columns filled with 1, and then the matrix Y is just some a random fill it but with shape 2 by 2. And if you want to add it, you just call torch.add method and input the two matrix. And when you print it, you can see the last one. The first one is X, the second one is Y, and with add just for it's just add them together. And also similarly, you can do subtraction by using torch.sub method, and multiplication by using torch.mm method, and torch.div this method. But for the multiplication, actually is the kind of like one of the most popular operation we used in deep learning, because in models actually what we are doing is some matrix multiplications, and so, but when you use this method torch.mm, it's only support float. So it doesn't support integer. The integer is like long tensor. So every time if you want to use this method, use this function, you have to convert the long tensor, which is integer, to float tensor by using dot float function. So for example, here I create a a tensor with a tensor x1 with shape 2 by 3, but here because this is integer, it is a long tensor, so I use dot float to convert it into float tensor. And for x2, because torch.once automatically is defined to create the float, so that is fine. You don't need to use dot floats to convert it to float tensor. And then when torch.mm, you just input x1 and x2. Another operation is useful is called slice. This is the same with Python slice or NumPy slice. So just to choose some subset from your matrix, from your vector. This one you can run it later. So this is to slice like all the rows but column 0, and this one means you want to for the row first but all columns, and this is element at row 1 column 1. Okay. But if you use this one, for example, x11 to get element at 1, then you can see it's return you a tensor. It's here. It says tensor, this value. But sometimes we don't want a tensor, we just want the number here. So what you can do is use dot item method. So you can see this time it's gonna return the number, it's not a tensor anymore. Another one is concatenate. So concatenate is you can so here, let's first define a tensor. Let's use torch.range arrange 6, and we reshape it into 2 by 3. And you can see this is the description. This is a tensor with integer. The d type is integer, and with shape 2 by 3, and the value 0, 1, 2, 3, 4, 5. And to do concatenate, it has a function called torch.cat. So torch.cat, and I input like now I just want to concatenate x and with x, and then you can specify the dimension. So dimension 0 means you want to concatenate on the rows. So you can see after it's become like from 2 rows to 4 rows. So it's become 2, 1, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. Definitely you can concatenate on the second dimension, which is a column. So you can see the original one is 2 by 3, but if you choose dimension equals to 1, it's become 2 by 6. So the resulting one will look like this. Okay. Stack is also concatenate, but a stack will give you a new dimension. So let's go back here. You can see for cat, no matter you choose dimension 0 or dimension 1 or 2, 3, 5 later, it's didn't generate a new dimension. So this is, you can see we have the original x, we have 2 dimension, right? It's 2, 3 is 2 dimension. The resulting concatenate is also 2 dimension, no matter you choose dim 0 or dim 1. But if you choose stack, it gives you a new dimension. So as you can see, now it's become 3 dimension. It's become a nested, the list of it's a nested list. So same if you choose dim equals to 1, it's also add another dimension. GPU support. So this is the important part. So for deep learning. So for deep learning, we know we're gonna deal with like huge data size, and your model can be also like need a lot of weight neurons to train. So if you use CPU, then it's very slow. So we need GPU to calculate in parallel. So before all the tensor creation or operation we see is based on CPU. But we can move them to the GPU if you have GPU. So they are usually this line is a very useful line. This is because sometimes you are not sure if you have CUDA or not. CUDA refers to the GPU. So we write this one, which means, so for the function torch device, if our device have CUDA, which you have CUDA, then I use CUDA. If I don't have CUDA, I don't have GPU, then I just use CPU. So this one, you don't need to go to check, okay, if my device CPU is available, you just use this line and it will automatically assign the available resource for you. And when you print the device, because now I'm using Colab, so Colab have GPU support, so it's CUDA. And if you want to know how many GPU I have, you can use this one. You can use this function torch.cuda.device count to see how many GPU you can use. And when you print, you can see for Colab only have one GPU, which is Tesla T4. Okay, and you have two ways to create a tensor with GPU. The first method is you create a tensor in CPU first, and then you use two device to move it to GPU device. So this is you create on CPU first and then move it to GPU. Another way is you can directly create them on GPU. So here, I didn't use .to device method. What I use is I use the device attributes in the function, and then I set device to here. So here I have CUDA, so this one gonna be CUDA. And when you create, when you print, you can see these two have the same result. So now, and we have another attribute here. It's called device equals to CUDA 0. So which means now this tensor is with GPU. But for the GPU support tensors, you cannot mix CUDA's tensors with CPU tensors. It will lead to errors. This is because we need to ensure the tensors are on the same device. So for example, in this cell, I already define X on GPU on CUDA, and now if I define Y is on CPU, and then I do the operation X plus Y, it will say expected all tensors to be on the same device, but find at least two devices. One is on CUDA, which is X. One is with CPU, which is Y. Okay. Any questions so far? Okay. If you don't have, let's move to next part. AutoGrad. So the AutoGrad package provides automatic differentiations for all operations on tensors. Generally speaking, in PyTorch, we don't need to worry about partial like these chain rules, anything like it. AutoGrad is PyTorch automatic differential package. This is what we just see before. It's a requires grant equals to true. So which means we want to set the vector to be learnable. So it's so during back propagations, gradients are calculated to show how much each parameters or the tensors contribute to the error in the model's prediction. And this gradients are then used to update the model's parameters, typically by applying and like optimization algorithms to improve to train the model neurons. So let's see the example. So first, like import torch, and here I create a tensor which is random, but I set required grade equals true, which means okay, x, this tensor should be learnable. And now if I do y equals to x plus 2, because how PyTorch is smart enough, so because you set x learnable, then PyTorch also know okay, y is also learnable because y is the operation result on x. So here you can see if I describe x, so x is this. X is a float tensor with shape 3. It's the value is like this, and required grades is true, means it's learnable. But for y, you can see for y, I didn't set the required grade equal to true. But when you print it, the grand fn is add backward, which means okay, it can track the operations on x. So which means from y to x, it's do the add operation. So every time if x update, y will also be updated. You don't need to manually set y requires grade equal to true. And also you do more operations on y because we know y is here. So y equals to x plus 2. X is requires grade equal to true, and y is also because PyTorch can track all the operations. And then if you would do all more operations on y, like z equals to y multiply y multiply 3, and then when we print z, you can say z grand fn is multiplication back. So which means PyTorch is able to track all the operations for the learnable vector, for the learnable tensor. Backwards. So backwards, another PyTorch function is to tell PyTorch to compute all gradients. We use the backward method. It will compute the gradients for all tensors involved in the computations of a given variable. So here, let's show you the example with code. So first, let's generate a data set of 100 data points, and I split into like 80% training, 20% testing or validation. This is the code. This code doesn't matter. It's just to create some random data points. And here, the result is I have training data X string, and Y string is the ground truth. It's a prediction. And also for validation, I have X validation, Y validation. And now let's use the pouch to see how we can train it. So first, this is we see before. We wanted to set it to the available resources. Like if we have GPU, then use CUDA. If it doesn't have, then just use CPU. So we write this line. And then you move your like X string, Y string, X well to the device available. So we can see this is 2 device. So if you have GPU have CUDA, then now X string tensor, Y string tensor is moved to GPU. If you doesn't have, it's just still with your CPU. And now let's assume XY is in linear regression. So linear regression is Y equals to WX plus B. So W, and now let's first just randomly initialize W and B because they are learnable, so that's okay. They will be updated during the backpropagation. So for W, the weight matrix, I randomly initialize it, and I say, okay, W is learnable, and this is the type, and this should with the, if we have CUDA, then it should with GPU, and B is a bias. So bias is I also randomly initialize it first, and I also tell PyTorch it is learnable, and this float and this device is GPU if you have, and then This is, if you print, you can see this just some random value that the PyTorch gave it, and this with CUDA, and for W, the weight matrix is also with CUDA, and it's learnable, okay? And then we can compute our model's predicted output, which is forward computation. So forward computation is for W, which we just defined here, which is learnable variable multiply X string. The X string is your input data, plus B. B is also a learnable variable, right? And then we're gonna have some prediction. So the prediction gonna be wrong for sure because W and the B are randomly generalized, but that's okay because they are learnable. Then you step 2, you compute the loss between the prediction Y and the ground truth Y. So you get the arrow. And because it's a linear regression, so for the loss function, usually we use is mean squared error. So this is the way to calculate the difference between ground truth and the prediction. And then we compute the gradients for both B and W parameters. And then after you run this, the B and W will be updated. They will not be these two default value anymore. It will be updated based on the loss, based on the difference between ground truth and prediction. Okay. So here you can see after I ran the back propagation, B changing, B from 0.1940 to minus 3.3881 is still with CUDA, and W, the weight matrix, from this value to this one. So you can see B and W are learnable. They are updated based on the back propagation. Any questions so far? All good? Okay. So the next part we're gonna is okay. So if you run this code again, okay, just exactly same one. I just again because I got the updated B, updated W, and if I run this one again, then it should be better than the previous prediction, right? And then I do the back propagation again to update B and W, and now if you print it, you will find the B and W is the grant is accumulate. So which means in PyTorch, gradients accumulate by default. This means if you call the backward multiple times without cleaning the gradients, they will sum up rather than be replaced. But why PyTorch behave like this? Because sometimes we cannot give all the data to the model because maybe the data is too much, like we have thousands or millions of data, which is very normal in deep learning. So it will accumulate grants over multiple smaller benches, which means we cannot give all the data to the models, so we split this input data to smaller size. So really we call it sub mini benches, and then perform on an optimization step once at the end of all sub mini benches. And why do we need sub mini benches? So like the example I gave, if at the beginning, if you say, okay, every time in the training, I give 128 training examples to the model, but my GPU is not this powerful. My GPU doesn't have enough memory to fit all the 128 examples at once. So I have to split this further. So make that maybe change this 128 to 64. And if 64 is still large, then I have to change to 32, or maybe 16 or 8 or 4. So in this case, actually the gradient should be accumulated, because we want to get the gradients. We want to get the gradients at the end after seeing all these 128 training examples. So PyTorch design like this. But in the training, after each epoch, after it's already see all the training examples, we don't want this gradients be stored. We want it to be cleaned up. You want to set it to 0. So you need to call this function. so dot zero function, to make the gradient to be cleaned up to be zero after every time it see the training examples after every epoch. So after you run this one dot zero and you print out, you can see the gradient become zero. Okay. Okay, so now actually we already see all the important concepts for training a deep learning models. Now let's put it all together. So first, let's set some parameters. For example, learning rate. So learning rate, let's just set it to 0.1 first, but this one is too large actually. Usually you should start with a smaller one, but let's take this one as example. And I assume I'm training a linear regression models. So I need W, the weight matrix, and the bias. So I set the bias. I randomly give one value because it's learnable, so it can be random at the beginning. And the required grant equal to true, which means it's learnable. And its D type is float, and I put it to the device available. If it's GPU available, then just give it to GPU. If the GPU is not available, then just with CPU. And the second learnable variable is W, the weight matrix. Let me note it down here. So here for this linear regression, X and Y, they are not learnable. They are your input data, right? X is your input X, Y is your input data Y. It's like the ground truth. But W and B, they are learnable. So that's why here you define W and B with required grant equal to true. And some other parameters we need to define is the number of epochs. So here, let's assume I want to train this model 1,000 times. And then for every time, I do it like so. I get the prediction from the forward computation, forward computation. So the prediction equals to B plus W multiply the X input data. And step 2 is to compute the loss. So the loss is the difference between the prediction and the ground truth. So this is the arrow. And then you get the loss. Then after the loss, okay, you got the loss, then you can compute the gradients for both B and W. So what you need to, so this is how to calculate the gradients. And then after you calculate the gradients, you do the back propagation to calculate, to update W and B based on the gradients. Okay. This one you can run the 3 attempts later. It's gonna give you different results. And then you can see what's the difference between them. So here I will not go through this detail. And let's go to the last part is training pipeline for PyTorch. So before the examples I gave to you is quite, we need to define the grants, we need to define the loss function, we need to manually clean the grants, but actually in PyTorch you don't need to do so. The PyTorch pipeline for deep learning is very mature. So I will show you how to do it here. So the typical PyTorch pipeline looks like this. It has 4 steps. The first step is you need to prepare the data set. So which is to wrap it in a data set or data loader class. This one we're gonna see it later. And the second part is to design the model. So design the model with all the layers. What is your input look like? What is your output look like? What's the hidden layers you have? And then you construct the loss function. The loss function and of the optimizer. And then after define all these things, you start to training. So during the training, you remember the first step is the forward computation. So it's get the prediction based on your first randomly initialized variables. And then you do the back propagation. So the back propagation can update the weights for the learnable variables. Okay, let's see the examples. So let's start with some easy data. Let's assume, okay, I have a data set and the data set is linear regression again. So here I use y, I assume my function should learn y equals to 2 multiply x. X is the input, y is the output. And the first line is also, I want to see what device I have. If I have GPU, use CUDA. If doesn't have GPU, use CPU. And then it is the training samples. I just manually created for easy demonstration. So here I have, for X input, I have eight numbers. And for Y is the corresponding output. So if it's 1, then Y should equal to 2 because my linear regression is Y equals to 2X. And if X is 2, Y should be 4, and so on. So if X is 8, Y should be 16. So this is just my training data. And then you also can create some test data to test your model. So here I just created my test data X equals to 5. It's just one number. I want to see how it performs. So this is how I prepare my training data and my test data. And now the next step is you need to design your model. So the design model, usually in PyTorch, you should have this structure. So this one, the class linear regression, it's just a name. It can be anything. You can call it my model, your model, and so on. It's just a name. But in the bracket, you have to have this one. So this one is a PyTorch build class. So which means, okay, I want to build my PyTorch deep learning models based on this class. So you have to have this one in the bracket. And then you're going at least you're gonna have two functions. The first one is called init. So the init, the first line is just you write it. Is for means in Python or Java, it refers to the superclass, and then you can define your layer in the init. So here, because it's a linear regression, so I only need a linear layer. So if you want to know what is linear layer, please go to the PyTorch documents, like how you define the input, how you define these two parameters. So this refers to the weight, which is the W here, refers to the W, so which is a linear layer. So here I only want one layer, so I only define one layer here. And the forward is the computation, the forward computation. So here X is the input, and given the input, it will input X to the linear regression layer and do the matrix multiplication. So the forward is all the calculation you want to have in the PyTorch. But definitely you can have other methods. So for example, I just define some like maybe helper function, just like Python. We define the function with self, and then the input can be anything like number or something, and then you write your function here, and you can call this function in forward or init. So it's same with Python. This Python class, you can have your own function as well. Okay, and then when you initialize the models, then you just give the class name. It's same with Python, the class name, and then pass all the parameters. So here you need input dim, output dim. So input size, output size, and the two device. Remember, you need to two device, make it to GPU or CPU. And then you can start training. So before your training, you need to define your learning rate, number of epoch, your loss function. So here you don't need to manually define your loss function. PyTorch have almost all the loss function you need. They have the library, you can go have a look. And then I just call this loss function from PyTorch. Optimizer also you don't need to define by yourself. PyTorch provide the optimizer library. So here I use SGD. And the input is all the model's learnable parameters, which is just the weight. And then the learning rate is this. And then I start training. So in my training for each epoch, I do the forward pass, which is model. Model is here. I gave the name here. So you can if you call it my model, it's just a name, right? Then here is also, it should be my model. It's just a name. It doesn't matter. And then I pass X. X is the input. And then this one will go to the forward method. So X, this capital X refers to the lowercase x here, and then the X do the matrix multiply the weight layer, and then gave you return result. So the y predicted is returned from here. Okay. And for the loss, because you already defined the loss functions, you just give, okay, what is the ground truth? What is your prediction? Let me change back to model because I use this name in my following code, so I will change it back. Okay, you calculate the loss, and then based on the loss, we can calculate the gradients based on the back propagation. So you just loss dot back propagation and use optimizer to update weights by using the optimizer dot step function to update the weights. And then remember, you need to clean up the gradients every time. Otherwise, it's just sum up all the time. And then this line means, okay, for every 10 epoch, I want to see the prediction result. So, and then after training 100 epochs, and if you print, you can do some prediction by using the models you just trained. And this time you give the X test. This is our test data, and you put it into model. So it's also go to the forward method. So this time the X here is the X test, and this do the calculation with the linear layer you just learned and return the result. So you can see here, the prediction before training, which means the model, the W just randomly initialized. And if we give input 5, the output just is a negative number. But actually what we want should be 10, right? Because our training data is y equals to 2 multiply x. And you can see after some training epochs, even though just 10 epochs, when you give x test x equals to 5 is already very close to 10, which means it's updating because of the back propagation. And the weight also see is very close to 2. And at the end, after train 100 epochs, and then you gave the x test 5, and its prediction is much closer to 10. Okay. So this is how you define your pipeline for training the model. Any question about the class here, how it works? Okay. So the only thing is a bit confused is because we know in Python class, when you want to call the function, you have to give, for example, the instance name dot the function name, right? For example, if you want to call the forward, looks like I have to give forward bracket and then I pass x. But in PyTorch, you don't need to. You just give the instance name and the bracket and the input. It will know you refer to the forward method here. So this is the difference between the Python class method calling and PyTorch, this forward class calling. Okay, then let's build your first simple neural networks based on these PyTorch functions. This part is just to load the data sets from a famous MNIST dataset. This dataset contains handwritten digits, which is commonly used for training various image processing systems. So this part I just loaded because they are famous and popular. So PyTorch have this library to save these datasets. So just to load them from PyTorch. And then you can see the data here. I give you the example. It's just look like this. It's each input, the X is an image with 28 by 28 pixels. So you can see it's like 28 here, and it's also 28 pixels with handwritten numbers. This is the X. And the Y is the ground truth. For example, this one, the first image is 7, so Y should be 7. And this one is 2, so the Y is 2. Okay. And then after you got the data, the next step, you need to define your neural network. So same. So here I call my class neural net, but definitely you can give it any name. So like my neural network, my first neural network, and so on. It's just a name. And then, but you have to have this one to tell the model, this one is based on PyTorch model. So this is some my deep learning models. And also in your init, you like Python class, you define all the parameters in this init. So for example, I have the first linear layer, and I have a activation function, and I also have a second linear layer. So this is in my model, I have 2 layers and then 1 activation function. And in the forward is how it compute. So which means in the forward, when I give the input x, it first go to the L1 I defined, and then the output, after got output, I put it to activation function to make it to nonlinear prediction. And then give this output, I pass it to L2, which is my second linear layer. And then I got output, then return it. Okay. And after you define your models, you can create instance for your Python class. So here it's just like the Python class instance. You write the name of the class and then give all the attributes based on what you have in the init method, and then to device to map it to GPU or CPU. And the loss function, because this is classification. So for classification, usually we use cross entropy loss, and this optimizer. So here I use ADAM. You can also try different optimizers. And for optimizers, you need to pass at least these 2 parameters. One is the model all the model learnable parameters. Another one is the learning rate. After you define all these parameters, optimizer, and so on, you can start to train the models. So for each epoch, you can see that here is different. As I have another line I don't have before, which is model.train. So this is mean I want to set the model to training mode. So you may have the question, I'm training the model. Why I have to tell the model is training? It's training for sure. It is because when you train the models, in deep learning, we may want to see the evaluation result after, for example, 100 or 10 epochs. But when you do the evaluation, actually it's not training, right? It means after you training, it means you want to use the training model to do the evaluation. It's not training. So that's why you have to use such this function to tell, okay, now this model is training, but later I want to evaluation, for example, every 10 epoch, I will say the model.eval. So now the model is not training. Even though I give you some input, you give me some output, but the gradients will not calculate it because it's for evaluation. So these two, you may need it if you want to evaluate your model during your training. Okay, so here I set the model equal to train, and I here use this one to record the loss for each epoch. And then I load the data. So here you can see it's also in my previous example, I don't have this line. It's because for my models, it's impossible to see the whole data set. It's too large. So I have to use the loader to split them into mini batch. So, and every time I load the mini batch, I got the images actually is the X and the labels as Y. And then I input X into the models. So it will go to the forward method you defined and then give you the outputs. Then you calculate the loss between the prediction and the ground truth Y. So it's here labels. It's from your data set. It's not, it's from your data set. It's the ground truth. And then you calculate the backpropagation, update your parameters by using gradients and the learning rate. And this two is, okay, this is to update, and this is to tell the model, okay, you can clean up the gradients because now I already finished the training for this round. And then you add the loss to the epoch loss. Okay, and this line means, okay, every 5 epoch, I wanted to see the training loss. So this is every 5 epoch, you print the loss. And this one means for every 10 epoch, I wanted to see how it perform on evaluation data. So it is for every 10 epoch, I set model.eval to tell the model, now you are not training. Even though I give you the input, you cannot use this input to calculate the gradients because it's evaluation. So it's model evaluation. And also you need to have this line to say, okay, also you no need to compute the gradients during evaluation. And then you write this, for example, here I'm just calculating the accuracy, and then you can get the result. So this is the output. And if you want to check the parameters, all the learnable parameters, you just model dot state direct dict is gonna show you the result. Also, after training the models, you can save the models to your local path. So you just defined your path. So here I just say the current folder, and this is my file name, but it have to be .pth. And then you use torch math function called save, torch save, and to save it into that path. And when you test, you can load your model that you just saved. But before you load, you have to create an instance. Create an instance class, and then to device, and then use load stake math functions to load what you just saved. And then for the testing, it's just exactly same with the evaluation. But this time, maybe during the evaluation, maybe you use a validation set, but during test, maybe you are using testing data set. Okay. So now the example you see is, okay, for the first very simple example, I use the y equals to 2 multiply x. This data set is easy, but for this for this DG image data size, is from PyTorch. But most case when you want to train the deep learning models, we want to load the data size from for example, from our device, from our computer. So which means you need to define the data set. So to tell the models, okay, what is the data set? What is X? What is Y? And every time you load the data, what is the bench size? So you need to define so you can look at these two class. I have give you the link. You can have a look, which is to how you define your own data size and how you define your data loaders. And after you define these two, and you just train your models. So for data size class is a class that wraps your data and tells PyTorch how to access individual samples. And you need to define these two methods. And you can think of it like a customer container for your data. And data loader is a class that loads benches of data for you, shuffle data if needed, and can use multiple CPU cores to load data faster. You can think it's like a pipeline that feeds data into your model efficiently. Okay. Okay. So I have exercise. You no pressure. If you wanna do it later, you can do it later. And then you have any question, you can email me. So the exercise is based on what we learn, you need to implement a PyTorch class model with 3 fully connected linear layers and 1 activation functions. And you need to use crawl entropy loss as a loss function, use ADAM as the optimizer, and train the model for 5 epochs, evaluating on the test set every 2 epochs. Oh, sorry, it's not the test, the validation set. The validation set every 2 epochs, and report accuracy on the validation set during training. And after the training, you need to report accuracy on the test set. And I give you the backbone of the code. So what you need to do is just to complete the to-do section in the code provided below to make sure your code can run. Okay. Okay, I will now pass this section to Pascal. But yeah, no pressure. You can do it up later. And if you have any question, just email me. Okay. Thank you.
Okay.
Okay. Thank you. So sorry, I have to go because I'm late for another meeting. Okay.
Okay.
Thank you, Pascal. See ya.
Thank you.